Okay, everyone, thank you for joining us here today for University of Texas Energy Institute's Energy Symposium for April 11th, 2023. Before I introduce today's speaker, I will highlight the next upcoming talk, which will be the last talk of the semester. So today is the penultimate talk of the semester. And next week, we will have our own Dean of the LBJ School of Public Affairs here at UT Austin, Jared DeShazo, and he will speak about job creation and electric vehicle adoption. But today it is my pleasure to introduce a colleague, and Gaël Giraud, and the title of his talk today is Extreme Climate Risks and Financial Tipping Points. A little background on Gaël. He's a former senior researcher in mathematical economics at CNRS, which is the French National Center for Scientific Research. He's a former chief economist of the French Development Bank, and he's the founder of the Environmental Justice Program at Georgetown University, where he now resides. His research is dedicated to what we would call stock flow consistent macroeconomics, integration of climate change and natural resources. A little bit of a background on what he's going to discuss today. His abstract designing climate change policies requires considering feedback loops between mitigation and adaptation, since more mitigation can trigger lower adaptation in the future. Many people think about carbon models, but carbon taxes, and today he's going to talk about his integrated assessment model, which has as you will hopefully learn, a different type of framework than most of the integrated assessment models you may have heard of in the past. He calls his model the IDEE, or Integrated Dynamic Environment Economic Model, but is fully coupled non-linear macroeconomic model and continuous time. So those are a lot of words there, and they kind of mean something for advances in this type of modeling. And we'll learn about that as we go. So he's going to discuss, as he shows here at the end, that provided public subsidies are high enough, a tax of $300 per ton of CO2 equivalent by 2030 enables reaching net zero emissions in 2050 and prevents firms from suffering global bankruptcy. So a lot of what he'll talk about is the financial aspects, which is to say the debt accumulation and interest payments that might be associated with an energy transition. So that being said, I will now stop sharing my screen and ask Gaël to share his screen. And as always, please ask questions in the question and answer feature of Zoom at any time. And we'll ask these at the end of the talk. And if there's a clarifying question, I'll try to interject. So Gaël, please go ahead.
Thank you. Thank you, Karen. Thank you for the invitation. So I'm going to share my screen, if that's okay. So you can see my screen now.
Yes, thank you.
Okay. And so, yeah, the work I'm going to present is still an ongoing work in the sense that there are plenty, many papers that we are writing almost at the same time in various directions using the same kind of methodology. So what I'm going to describe today is maybe the core of this methodology and one application, which is this paper that I wrote together with Hugo Martin, Aurélien Quiquet, Sylvie Charbot, Didier Roche, and Timothée Nicolas, who obviously are French researchers, whose title is Extreme Climate Risks and Financial Tipping Points. But I guess for you, the most interesting is the methodology. So let me start by just saying that macroeconomics today, at least in terms of as an academic field, is in a kind of very disturbing situation in the sense that since 2016, there has been a lot of leading economists claiming that macroeconomics today is really no longer a science. So probably the first guys who said this in a very clear way was Paul Romer. At this time in 2016, he was still the chief economist of the World Bank and hadn't yet received the Nobel Award. And he published a paper whose title is The Trouble with Macroeconomics, which is an allusion to the book by Lee Smolin in Theoretical Physics, The Trouble with Physics, where essentially Paul says that macroeconomics has gone backward in the past 40 years. So I can enter into the details if you're interested in, but essentially, to a certain extent, what I'm going to present to you and what I'm working on, including with you, Carrie, is a kind of alternative to what Paul Romer is criticizing. Then, in the same summer, 2016, you had Olivier Blanchard, who had just retired from his position as the chief economist of the IMF, who also wrote a small paper called On the Future of Macroeconomic Models, where he wrote explicitly, I quote, DSG models are flawed, are basically flawed. So DSGE is an acronym which stands for Dynamic Stochastic or Dynamical Stochastic General Equilibrium Models. I will say a few words about these kind of animals in a few minutes. And then you had an op-ed by Paul Krugman, who received the Nobel Award, of course, as you know, whose titled The State of Macro is Sad, essentially summarizing what those guys, Paul and Blanchard, had said earlier. And you also had a very interesting post on his blog by Narayana Kocherlakota, who back then was the governor of the Central Bank of Minneapolis, Minnesota, which is sometimes considered as being one of the meccas of, neoclassical mainstream economics. So Kocherlakota wrote in the same summer, 2016, a post saying that we are dealing with toy models which are very far away from reality. And if we want to fix these models, it will not be enough just to change a few epsilons. We have to start from scratch again, or almost from scratch. And that's what we are going to do in this presentation. At the same time, it happens that you have a number of critiques which are expressed by other economists, not so much on the core of macroeconomic theory, but on its interaction with climate change. So you have Nicholas Stern, of course, who is very famous, the former chief economist of the World Bank, Joe Stiglitz, and myself and others, who wrote papers saying, most IAMs, so integrated assessment models, are completely flawed. And it's not a surprise if you have someone like Bill Nordhaus, who got the Nobel Award, who keeps repeating even today that if we experience something like plus 6 degrees Celsius as an average global warming on the planet, let's say at the end of the century, this will only cost like 10% of the real world GDP, which is ludicrous, because if you know a little bit of climate science, plus 6 degrees means apocalypse on Earth. So the big question is, how come that so many mainstream economists keep repeating these kind of completely insane statements? And I'll try to give you a kind of intuition for that in the coming 20, 30 minutes. So there are some alternatives to that. I will briefly say a few words on about this, namely the agent-based models. But let me just first try to give you a flavor of why macroeconomics is in such a bad state today. So this chart gives you two things. So the red curve is the public debt of the US. And as you know, the public debt, the sovereign debt of the US increased a lot after the global financial crisis of 2008. So that's the red curve. And then the blue curve is what we call the spread, that is, the increase of the interest rate charged by financial markets on the sovereign US Treasury bond because of its riskiness. And normally, according to all, but absolutely all neoclassical mainstream economic models, if the public debt of a country increases so rapidly, like this one, then its riskiness increases, and therefore its spread should increase as well. And we observe exactly the opposite. So the spread is declining while public debt is exploding. So this is one of the paradoxes that mainstream models are absolutely unable to explain. Another one is this one, also very famous. So the blue curve here, that's what we call M0, which is the most basic monetary aggregate. So that's the quantity of money created by the Fed in the US. And as you know, in the aftermath of the global financial crisis, so the Fed printed, quote unquote, a lot of money. So you have QE1, the quantitative easing number 1, which is here, if you can see. QE2 is here, QE3 is here, and each time the Fed has literally created billions of dollars in order to save the banks. Now, here, normally, people would say that if you print a lot of money, and especially if you do it very rapidly, then this would have an inflationary effect. And that's one of the reasons why we have this debate today about inflation and the causes of inflation, where you find a number of economists claiming that this is due to the fact that during the pandemic, during the lockdown, the Fed printed too much money in the direction of, let's say, poor people. I don't believe at all. I mean, I don't trust at all this kind of explanation. And one counterexample of this is this chart, because here you have the consumer price index in the US at the same time. And so if it was true that printing billions of money necessarily leads to inflation, then given the increase of the blue curve, we should have a tremendous increase in CPI, the consumer price index, and we don't have it. So which means there is something wrong in the statement that this equation, which is a kind of, let's say, tautology, where you have capital M, which is the aggregate quantity of money, V, which is money velocity or the velocity of circulating money, P here, which is the average price level, and capital T, which is the volume of transactions, so that PT is nothing but nominal GDP. So many, mainstream economists interpret this by saying that in the short run, V is constant, capital T is constant. Therefore, if you increase capital M, you must increase small p, the level of prices, approximately proportionally to the increase of capital M. And so this interpretation I'm saying is completely wrong, because here you have a counterexample of that. M0 is exploding, so capital M is exploding, and at the same time, P remains constant, more or less. There is no trend in P. So it's just not true that printing more money necessarily leads to inflation. Maybe the truth is that sometimes it does lead to inflation and sometimes it does not. And the question is to understand when, of course. And if this is true, this means that the origin of inflation today might not be linked to the monetary policy of the Fed and the White House during the pandemic. Another example, which is very striking, is this. So this is the price of oil, and probably the most important price on the entire planet today is the price of a barrel of oil, because everybody needs to know this price. And here you have the expectation of the oil price by the International Agency of Energy, or the International Energy Agency, IEA here. And so this is the historical time series of oil price. And for each point here, that's the anticipation by IEA of this price. So what you see here is that each year, IEA is completely wrong, each year. So it's not that we would be learning slowly how to anticipate prices. We don't learn anything. Each year, we are completely wrong. So then the main question is, how come? How come that IEA, which probably hires the best energy economists, is not even able to anticipate the price of oil in the next few months? And this constantly, it's a chronic disease. Similarly, you have another problem here, which is the anticipation of GDP. So that's for Greece. You know that Greece was subject to a very harsh structural adjustment plan between 2010 and 2015, imposed by the IMF, the European Central Bank, and the European Commission. And so between 2007 and here 2011, this is Greece's GDP, so which is falling down, free fall, literally. And each time the IMF makes an expectation, a forecast about the evolution of Greece GDP. And here this is a forecast each year. So each year the IMF is completely wrong, deeply wrong. And each year the GDP of Greece is going down further, and each year the IMF keeps repeating, no, it's okay, it will come back to its earlier stage. And then the question again is, how come? How come we might be so wrong in just anticipating the GDP of a small country like Greece, or anticipating the price of the most important commodity on the planet, or just understanding the impact of creating money in the US economy, or the impact of increasing US sovereign debt on financial markets? How come we might be so wrong? And so to a certain extent, what I'm going to suggest is that we are deeply wrong, because one of the reasons for that is that we begin, most mainstream economists, including myself, when I was writing mainstream economics papers in mainstream journals, we always begin by postulating that the economy is at equilibrium. Whether you do mathematical finance or general equilibrium theory or standard micro, standard macro, or game theory, you always assume that people are going to play an equilibrium. be it a variation equilibrium, a Nash equilibrium, which to a certain extent is equivalent to a variation equilibrium, etc., etc. By contrast, there are a number of people, and originally these were physicists, and it's not a surprise, who started, with the very famous Santa Fe meeting in the 80s between physicists and economists, who said, well, actually in real life, we are never at equilibrium. We may converge more or less slowly towards an equilibrium, and that's the example of the very famous El Farol bar. I think it's in San Francisco or Los Angeles, I don't remember. Namely, in any case, it's in California. So it's a bar which is very famous, where many people like to go at the end of the day, and it's a bar which is somewhat small with respect to the audience or the population that might go to this bar every day. So if there is more than 60% of the population in the neighborhood which goes at the same time to this bar, it's overcrowded. If there is less than 60%, you still have some room in the bar. And so this is a simulation, this is a random simulation of how people can learn whether they should go to the bar or not. And obviously, everything should happen as if people would toss a coin, a biased coin that would tell them with probability 60% you should go to the bar, and with probability 40% you should not go to the bar. And everybody should have an independent coin that he or she would toss every day in order to decide whether he or she goes to the bar. So game theory standard game theory would assume that everybody coordinates spontaneously on a Nash equilibrium, a mixed Nash equilibrium with random strategies. But of course, this never happens in real life. And so this is a simulation of how people slowly learn to coordinate on the 60% threshold. So in macroeconomics, actually, there was actually in the 50s, 60s, an idea that came a little bit in this direction, which was the famous Solow model, which I just remind here. So there is a single equation. It's a differential equation here, where you have the evolution of capital, which is the key variable in this model. So the evolution of capital is simply investment, and investment is simply saving, and saving is simply a fraction of production here. So small s is a real number between 0 and 1, which captures the fraction of production which is dedicated to saving and therefore to investment. Minus what? Well, the depreciation of capital, small delta, the evolution of the growth of the population, small n, and the growth rate of technology, small alpha. And so this single equation gives you a dynamic which is not completely uninteresting, which is for which you have a graphic illustration here, and which essentially says, well, there is a single long-run steady state, which is an equilibrium, which is globally stable in the sense that wherever you start in the economy, you will always converge to that equilibrium, that single equilibrium, and everything will be fine at the end of the day, provided you can wait long enough so that you can reach this single and unique globally stable equilibrium, the Solow equilibrium. And so in the 50s and 60s, this was a kind of, big news, because so far the main macroeconomic model people were familiar with had been conceived in the 30s by two guys now called Harrod and Domar, which was saying exactly the opposite. So the Harrod and Domar model, and Harrod and Domar were Keynesian people, was saying, well, there is a big instability in the economy, and there may be an equilibrium, but it is intrinsically locally unstable. Meaning, if you don't start at this equilibrium in your model, you will never converge to this equilibrium. So they were claiming in the 30s, and we can understand why, historically speaking, that capitalism was intrinsically unstable. And so Solow's model was viewed as a kind of alternative, saying, no. If you write things properly, you will see that actually capitalism is stable, and we are all peacefully converging to a globally stable, unique equilibrium. So to a certain extent, the family of models that we are working on uses the same kind of methodology as the Solow model. So it's a continuous time macroeconomic model where we describe the motion of an economy thanks to a differential equation, or sometimes a PDE, a partial differential equation. And we try to study what we call the phase space of this economy. That is maybe the set of equilibria. Maybe there is not just a single equilibrium. Is it globally stable, locally stable? What are the chances that we are going to converge to this equilibrium? Is it profitable for everyone to converge to this equilibrium, et cetera, this kind of question. For that purpose, we need to take into account that there are a number of facts which are also completely unexplained by standard mainstream macroeconomic theory. And the first, probably the most important of them being the increase of inequalities, which you can capture, among other things, by the decline of the wage share, small omega. So the wage share is the fraction of GDP which is distributed as wages. And here, as you can see, that's the blue curve here, it's declining for years and years. And so this stands in sharp contrast with what was claimed by many mainstream economists, including someone like Kaldor, who was a Canadian in the 70s, because they would claim that omega was constant. That is, well, you know, the distribution between profit and labor would be constant, and this would be a kind of law of capitalism. And now, since a couple of decades, we see that this is no longer the case. So we have to take into account the fact that omega is not constant, and even more, as we'll see in a minute, that there seems to be a kind of cycle that is followed by omega, okay? The next point is this, which is work done by one of my former PhD students, Florent Maquisac, who is now working for the World Bank. And so here, Florent has plotted two variables, omega, the wage share, and lambda, the employment rate. So omega is the x-axis here, and lambda is the y-axis. And this is for the US between 1948 and 2017. And you have three regimes. So he statistically proved that there are three regimes during this period where you have a structural break of the dynamics of both omega and lambda between each of these regimes. And now if you plot the graph of the evolution of these two variables, you see that if you take into account these three regimes, everything goes as if they would cycle around this equilibrium here. You see? That's the second regime, and that's the last regime. So for the last regime, there is something very weird happening just in the few recent years, which is that lambda seems to be declining and omega seems to be declining at the same time, so that we get the impression that they have lost the cycling properties. I will return to this later on. But otherwise, if you just forget this branch here, which is a kind of pathology, you see that essentially the economy is cycling over a kind of fixed point. Okay, that's exactly the intuition that we will illustrate, starting with a very famous model from the late 60s, which is due to Richard Goodwin. Now, another point which is worth mentioning is that the Shortrun-Phillips curve is still alive, as Greg Mankiw repeated in 2019. So the Shortrun-Phillips curve would tell you that there is a link between the growth rate of money wages and the employment rate, in the sense that if you have less unemployment, so if you have more employed people, in other words, if the ratio between employed people and working population is increasing, then it becomes easier for those people who are employed, for employees, to bargain a rise of the pay wage. Why? Because, well, you know, there are less and less people who are unemployed, and so the employer, you know, has to bargain. While on the contrary, if you have more and more unemployed people, it becomes more and more difficult for employees to bargain an increase of the pay rise. Why? Because if they are unhappy, the employer can say, well, if you're unhappy with me, you can go outside. There are so many people who are waiting for to take your job. So, you know, so, and this is what we observe. And so here you have an illustration of that. So the blue curve is the employment population rate, here, as you see here. And the green curve is a proxy of the evolution of wages. And as you see, they follow quite closely the blue curve. So so I don't have to go into this. So now we are equipped with a number of ideas in order to try to solve the problems that had been highlighted in 2016 by Paul Romer, Olivier Blanchard, and a number of other economists. These intuitions are what? First, as I said, the Phillips curve is still alive, so we have to take this into account, and this provides a bridge between the evolution of wages and the employment rate on the labor market. Second, there seems to be a cycle between the wage share and employment rate here. And third, the wage share is definitely not constant, okay? And fourth, well, probably the economy evolves according to some differential equation in continuous time, analogous to this one, which has been conceived originally by Robert Solow, okay? Now, so the alternative that we are building, in order to explain it, let me just remind you, so omega is the wage share, lambda is the employment rate, alpha is the growth rate of progress, of technology, technological progress, delta is the capital depreciation rate, and beta or n, depending upon the paper, is the growth rate of labor forces, and nu, which is a new variable, is the capital output ratio. Why? Because we are simply going to assume that GDP, Y, is the minimum between this ratio, where you have capital here, divided by nu, and this product, which is just labor, the quantity of hours worked by employees times labor productivity. And we will make the assumption that entrepreneurs are not stupid, so they hire enough people so that the two terms here are equal. So actually we have y equals k over nu, which is also equal to LA times capital L. This means that nu is nothing but the capital to output ratio, which was also thought of as being constant for decades. Now, if you take the ingredients that I mentioned earlier, you will easily end up with a two-dimensional dynamical system, which is here, which is the original dynamical system introduced by Goodwin in the late 60s. So here you have the evolution of the wage share, and it's given by this, where here you have the Phillips curve, that is the evolution, the growth rate of money wages minus labor productivity. In other words, if, let's say, if wages increase more rapidly than labor productivity, then this means that the wage share will increase, which is quite natural. In the same way, here you have the employment rate, and what these equations tells you is that the evolution of employment rate should be equal to investment, which is this ratio here, minus the depreciation of capital, the evolution of the population, the working population, and the growth rate of labor productivity, which is also obvious in the sense that investment here turns out to be exactly equal to the growth of the economy. So if the economy grows more rapidly than everything that is decaying here, that is depreciation of capital, growth of labor, and labor productivity, then employment will increase, and the employment rate will increase, okay? So now you have a two-dimensional dynamical system, which is very simple, and it happens that in this dynamical system, you have a single equilibrium, but which is not locally stable. So we are close to Solow's idea, except that the unique equilibrium is not such that the economy would spontaneously converge to this equilibrium. The next point is that we have to acknowledge that the capital to output ratio, so the small mu, which is here, is far from being constant in real life. Here you have the capital to output ratio for the US, and you see it's not constant, obviously, between 1950 and today, more or less. So we need to take into account the fact that there is probably an endogenous variation of nu, and even you can see it's also a cyclical evolution. There seems to be a cycle followed by nu. In order to take this into account, we will have to replace the Leontief production function, which is here, by a more sophisticated production function where you have some substitutability between capital and labor. I will go to this in a minute. Another point that we have to take into account is the role of debt. So in 2016, McCourt, who is a very iconic, he was the iconic governor of the Central Bank of England. And actually, sorry, this is a mistake. It's 2015, just before the COP21. He said that, we might experience a climate Minsky moment on a financial sphere, in the sense that we may have a big collapse due to a pro-cyclical crystallization of losses in the financial economy because of an excess of debt. And so far, at least until 2012, most mainstream economists would claim that debts don't really matter. Why? Because if there is someone who has debt, let's suppose that I have debt, and that there is an economy populated by two people, so Carrie and myself. So if I have debt, so Carrie must be the creditor against me. So when we average between Carrie and myself, on the average, both my position and Carrie's position will cancel each out, and so that should not matter. And then, thanks to the global financial crisis of 2008, macroeconomists discovered that debts actually do matter, and so that's why we will have to introduce debts in our economy, in our model. So this is an example of the evolution of the private debt to output ratio in the US, because we speak a lot about public debt, but the main idea here is to say, well, actually public debt is not the most important thing. What matters really is private debt. So here you see that it's far from being constant, it's even increasing tremendously. Same story for a number of other countries like Japan, like Spain, so the US again, the UK, etc., etc. So I don't have time to show this. So now we have a number of ingredients. We have the fact that we have, the Goodwin model, the two-dimensional dynamical system I was showing you, which takes into account the fact that the Shortrun Phillips curve is still alive, so there is a link between employment and the growth rate of wages. And on top of that, we want to take into account the fact that the capital to output ratio nu is not constant, and that private debts do matter. Now, in order to cast all this within a single framework, we want our whole story to be stock flow consistent. What does this mean? It means that at each point of time, we want to make sure that the stocks of our economy are exactly the output of the history of flows. Because if this is not the case, this means that there is some inconsistency in the way we have modeled our economy. So here you have an example of the way we make sure that we are compliant with the stock flow consistency requirement. So this is a kind of balance sheet of the economy where you have households. This is the column of households. This is the column of firms here, and this is the sum. So a very simple economy where you have only two types of actors, households and firms. So households, they receive wages. So that's an income for them, which is an expenditure for firms, which are paying wages. What do they do with these wages? They pay consumption. I mean, they spend money for consumption. This is now an income for firms. At the same time, what do firms? Firms also invest, so they have to pay money in order to finance investment. But since there is a single sector of firms, this is also an income for the firms which are receiving that money to invest. They also lose money because of the depreciation of capital, so they have to repay in order to compensate for this depreciation, etc., etc. And so by taking all this into account, you have a kind of skeleton of an economy. And the main point is to flesh this out by describing the differential equations that are followed by these variables, like consumption here, wages, investment, etc., etc. Okay? So in other words, a stock flow consistent macroeconomic model is a model which starts with this balance sheet and then fleshes it out with differential equations, okay? So since time is running, I won't have time to go into all these details. I can answer your questions if you want. Now, if you add a variable capital to output ratio, you will see that in the very simple two-dimensional model that I described earlier, you do recover a unique equilibrium, which is the solo equilibrium, and the economy cycles and converges toward this equilibrium in the plane where you have as x-axis omega, the wage share, and as y-axis, the employment rate lambda, okay? So to a certain extent, if we don't introduce debts, then we are back to the familiar solo story narrative that there is a single equilibrium which is globally stable, okay? Now, if we add debts, the situation is much more complicated. So here, this is another illustration of how this whole story works empirically. So this is due to Matthias Grasselli, who is a common friend to Carrie and myself. So this is Germany from 1960 and 1990. So here you have again the wage share on the x-axis and the employment rate on the y-axis, and you see that the economy is cycling like this around this point, which is the equilibrium. So everything goes as if we would be either in this situation with a variable capital to output ratio, or in this situation with a constant capital to output ratio, where the equilibrium is still here. In this situation, we cannot converge to it, as I said. The equilibrium is not globally stable. Here it is. So, of course, empirically speaking, we cannot assess whether at the end of, the history of the universe we will converge to this, but at least we are sure that there is this kind of cycle around an equilibrium. Now, if you add that, you end up with a three-dimensional dynamical system, which is much more complicated, and there are a number of papers trying to deal with this. So one illustration of that is here. Here again, you have the x-axis with the wage share. Here now you have the employment rate. And now the z-axis is small d, which is just a ratio between private debt and GDP. So in this theoretical example, the economy starts here. It cycles, so you have endogenous business cycles. At the beginning of the story, small d increases, meaning that private debts increase more rapidly than GDP. Here it seems to stabilize, meaning that now small d remains constant, and then small d declines, fortunately, and the economy converges towards this very long-run steady state here, okay? Now, a number of people have tried to empirically assess whether this type of dynamics makes sense, empirically speaking, and the answer is yes. It performs much better than the mainstream macroeconomic models. So, for instance, you have so Mateusz Caselli and Maishwari, they have shown that actually it works very well using this kind of approach here that I showed here. And then Florent Maquissac, my former PhD student, whom I already mentioned earlier, performed backtesting work, which is to backtest this family of model against a VAR. So for those who know what it is, a VAR is a very universally used short-run macroeconomic model that is used by every international institution like the Fed, the IMF, the World Bank, the ECB, etc., and which is considered as being the golden standard, at least in the short run. And what we show, what Florent shows actually is that our models perform better than a VAR even in the short run, not even mentioning the long run, but everybody knows that in the long run, a VAR is completely wrong. So which means that capturing these kind of dynamics actually enables us to capture, even in the short run, where you would suspect that non-linearities don't really matter, actually they do. So this enables us to capture much better the nonlinear dynamics of an economy than everything that is available so far. So the general properties of this approach are that private debts matter, obviously, that you have endogenous business cycles, that you have multiple equilibria. So in contrast with what you see in the solo model, where there is a unique equilibrium, now you have multiple equilibria. Among them, there is one equilibrium which is nothing but solo equilibrium. So it's a balanced growth path where everything is fine at the end of the day. But unfortunately, you also have a very bad equilibrium, which is a debt deflationary equilibrium with bankruptcy, where you have an overhang of debt, which drives the economy towards a catastrophic long-run stationary state where essentially you have no production, 100% of unemployment, and no wages. And so that at the end of the day, you have the traditional Phillips trade-off in the long run. Either you accept that there is a little bit of inflation and then you have a high employment rate, that's the good equilibrium, or you definitely don't want to have inflation, but then you have a high degree of unemployment and you end up in a debt deflationary trap. Other properties is that I published a paper with Mateusz showing that if you have too wide income inequalities, then your economy will end up into this catastrophic deflationary equilibrium. I have another paper which is not yet published with one of my other PhD students, Eduardo Seto, which shows that you can introduce money in this kind of model, and money turns out to be non-neutral and endogenous for those who know what it means. We are working on the multidimensional setting with Paul Valk here in Washington, DC. And of course, you can embed all this into a thermodynamical setup, which is done by my other PhD student, Grégoire Noël. So now I just want to spend the next few minutes talking about climate. So just so the interaction between this family of models and climate. So just to give you a flavor, if you look at this model, you see that here there is this equilibrium, and everything goes as if, your economy will be like a ball, as if you would play golf. It goes here, and then here it is trapped in a crater, and it will end up at the bottom of the crater. Okay, so this is the metaphor that I would like to use here. Suppose you would play golf on the moon, and so there are craters here, and if your ball is trapped here, it will end up at the bottom of the crater sooner or later. That's an equilibrium. But you may also, the ball may also end up at the top of the hill here. If this is the case, obviously this is an unstable equilibrium, because a little bit of, a small shock, however infinitesimal, will push the ball outside of this equilibrium. So there are a number of stable equilibria at the bottom of each crater, and the question is, where does the economy ends up? Okay, so here you have a simulation of the crater of an equilibrium. This is a simulation by Matthews. So here is the equilibrium. You have the wage share here, employment rate here again, and the debt to output ratio here. And the blue geometric object here, that's the crater. That's the basin of attraction. That is, it's the set of points where if your economy or if your ball ends up somewhere here, it will ultimately necessarily converge to this equilibrium. Okay. Now, what we have done is that we have coupled these kind of dynamics with the climate models. First, we have done it with a very small climate backloop, which is used by Bill Nodals. So it works as follows. So you have, let's say, an increase of GDP, real output. This will increase CO2 emissions, which will increase the accumulation of CO2 in the atmosphere, which will increase the radiative forcing on the planet, which will increase the temperature. And the temperature will decrease the output and the capital, because it will destroy, as we know, thanks to the rise of the sea level, more storms, El Nino effects, heat, humidity, etc., etc. And so you have now a backloop of the increase, growth leads to a higher temperature, which leads to less GDP. For that purpose, we need to understand more precisely this arrow here, which links an increase of temperature with the loss in terms of outputs. There are several options. We have used 3 of them. The blue curve here is the Bill Nodals damage function, which tells you, as I said earlier, if you have plus 6 degrees of increase of the average temperature on Earth, you will lose only 10% of the world real GDP, which is ridiculous. But fortunately, you also have the damage function by late Weizmann, who claimed that an increase of 6 degrees would lead to a loss of 50% of the world GDP. And then you have the Dietz and Stern damage function, which says that an increase of plus 6 degrees will lead to plus 90%. So we are agnostic about which damage function is the true one, even though I truly believe it's somewhere between the red and the gray one. But anyway, we have performed a number of simulations using the 3 damage functions. And what we have shown essentially is the following. On the left here, so here you have again the wage share as a x-axis and the employment rate as a y-axis. And of course, we should add debt. So we haven't done it here for simplicity. And the economy starts here, and you see that the economy is cycling and converging towards the good equilibrium, which is close to 60% of wage share at the world level, which is not that bad, and something like 72% of employment, which is good at the world level. But then, unfortunately, climate change pulls the economy out of the crater here of this equilibrium, as if you would take the ball of on the surface of the moon and you would put it elsewhere. But here, fortunately, the damage function is weak enough that it's the Nodals damage function, so it's the blue one here. It's weak enough so that the economy converges back to the good equilibrium. In other words, market forces are strong enough to pull back the economy towards the good equilibrium. By contrast, here we have used the catastrophic Dietz and Stern damage function, which is this one, the red one here. And what we see here is that, again, the economy starts cycling around the good equilibrium, but then, unfortunately, climate change drives the economy outside of the basin of attraction of this good equilibrium towards a catastrophic equilibrium where there is no production, big collapse of the world economy here, okay? Moreover, what we have shown is that even the geometry of the surface of the moon is shaped by global warming. So this is the good equilibrium as a function of temperature. So if it's green, it means no increase of temperature. If it's red, a huge increase of temperature. And we have located it as a point in the three-dimensional space with, again, the wage share here, the employment rate here, and the debt ratio as a z-axis. And as you see, the hotter the planet, the less interesting is the good equilibrium, because then it means that you have less and less wages, more and more unemployment, and more debts. In other words, if you go back to my metaphor here, it means that, you know, the crater itself is changed because the equilibrium is moved by global warming. The situation is even worse because we have shown that the size of the crater itself shrinks as the planet becomes warmer, hotter. So this is the crater of the good equilibrium, the basin of attraction of the good equilibrium, and that's the basin of attraction of the good equilibrium with global warming. Here, no global warming on the left, global warming on the right. And you see the crater is much smaller. So it means it's much harder to reach the crater, the basin of attraction of the good equilibrium. So which means that the dynamics that we are facing now is completely shaped by the interaction between macroeconomics and climate. So I will stop in 2 minutes. What I want to show you now to end up with this is, so the paper, the last paper, now we have coupled this macroeconomic dynamics with a true climate model, which is a medium-sized climate model, which has been conceived in Europe by French and Belgian researchers, which provides you with, which is called I Love Clim, which provides you with information every 50 kilometers on Earth, and which is a medium size in the sense that one run lasts for 1 century, lasts something like 20 hours, okay, which is much better than the big global climate models for which one run lasts like something like 3 weeks. So here, this is just a confirmation of that our model is completely compliant with the IPCC scenarios. So we reproduce completely faithfully the standard in the climate change community. This is the skeleton of our economy. I don't have time to enter into the details, but I can do it if you want. And then we have fleshed it out with a number of equations, dynamical equations, which describe how the economy evolves with climate change, private debt, employment, etc. We have introduced bankruptcy. I don't have time for that. What I want to show is this. So this is from a paper by Murrah, Nature 2017, and it says the following. Here you have the average temperature, and here you have the average humidity during the day. And the red curve here is the curve of combinations of heat and humidity, which are little for an average human body. So not for Kerry, because I know, Kerry, you're very sporty, but for us humble mortals, you know, if we are somewhere here, we are just dying if we're exposed to this more than 6 hours. And I'm sure you all have made the experience that it's much harder to do your jogging in the jungle of Vietnam than in the desert of, let's say, Sahara. Why? Even though it's much hotter in the desert, well, the difference is that the desert is dry. And so the average, the humidity is close to 0. So you must be very, very hot before you reach this deadly threshold, something like 50 degrees Celsius. While in the jungle of Vietnam, the average humidity is something like, you know, between 30 and 40%, which means already if you have 35 degrees Celsius, which is a common temperature in Vietnam, this might become deadly for your human body. So the question then is, where will people be exposed to these kind of little combinations of heat and humidity? And this is a map from our last paper, which shows if we just follow the business as usual scenario, which leads us to something like plus 3.5 degrees Celsius at the end of this century, then this will be the situation on the planet. So the color means that if it's dark red or brown, you will be exposed to daily, lethal combinations of heat and humidity pretty much every day. If it's orange, like this every second day. If it's yellow, every third day, you see. So which means that the entire Amazon basin will be uninhabitable. Central America will be hell on earth. The southeastern coast of the US will be exposed to lethal combinations of heat and humidity every third day. So it will be very hot in Louisiana, Florida, etc. The Guinea Gulf will be a very complicated place to survive in. India is condemned. At least every second day, people will be exposed to lethal combinations of heat and humidity. And the entire Southeastern Asian subcontinent is condemned, especially Indonesia. And the eastern coast of China is in a very bad shape. So you have at least every third day, these kind of lethal combinations. And here, which is the place where you have Shenzhen, Hong Kong, in front of Taiwan, then people will be exposed to these lethal combinations of heat and humidity pretty much every second day, at least, if not every day. So that's one example of what we can do with our model. Of course, with a mainstream model, you can never do that, because in a mainstream model, you are at equilibrium no matter what, and there is no money. There is no link to climate change in the way we have done it here. Why? Because this climate model, Isle of Clim, that I just briefly not even described but mentioned earlier here, it is built as a dynamical system, of course, a non-linear dynamical system. And standard mainstream economic models are static equilibrium models. And you cannot just couple a static equilibrium model with a dynamical system. It just doesn't make sense. So for the coupling to make sense, you need to rewrite your macroeconomic model as a dynamical system, which we have done, and then you can try to couple them. And then you can end up with this kind of very, very gloomy picture. Of course, the good news, picture like this, yeah. The good news is that there are ways to avoid that. So this is what we study in our paper. We can end up with a much less catastrophic situation, like here, or like here, etc., etc. I don't have time to enter into the details, and maybe the details are not the most interesting point. So the main takeaways of this paper, and I will stop here. First, in order to avoid the catastrophic map that I was just showing, we will need a lot of private investment. So that's the last line here. We agree with the last new climate economy report by Nick Stern by 2018. We also end up with an estimation of a need for 90 trillions of US dollars by 2035 in order to have a reasonable chance to remain not too far away from the +2 degrees Celsius threshold at the end of this century. And so this is an order of magnitude of the world GDP today, which is 100 trillions approximately. And so this means a lot of money. The private sector will have to fund part of this. There is no other way. But then we need to make sure that the dynamics of private debt does not lead the world economy towards a kind of catastrophic equilibrium. And what we have shown is that if we don't do this quickly enough, and if we end up somewhere in this very dangerous interval of global warming between +2.3 degrees Celsius and 3.5, then the chance is very high that we will reach a financial tipping point where it will become impossible for private firms to both address the cost of mitigation, reducing greenhouse gas emissions, and at the same time, adaptation to global warming. Because if we are in this range, then global warming will destroy a lot, whatever being the damage function that you use. And so many firms will have to spend a lot of money just to repair capital, to repair infrastructures, to rebuild plants, to rebuild cities, etc., etc. And so entering into this is very dangerous, not quote unquote just for climatic reasons, but also for purely macroeconomic and financial reasons, because here we enter into a zone where the world private sector might go bankrupt. How to avoid this? First, we need a very high carbon tax. So what we show is that if we have something like $300 per ton by 2030 and $400 per ton by 2050, at the world level, then this is necessary in order to avoid a catastrophe. Plus, we need public subsidies. So the public sphere has to step in and to be in charge of at least 50% of abatement costs. The good news is that this public spending never exceeds 10% of the world GDP. So today, on average, public expenditures represent something like 20% of the world GDP on average, much more in China, much less in the US. And so we would jump from 20 to 30%. So some people might say, well, this is North Korea, which is not quite true, but anyway. But at the same time, our contention is to say, well, if this is the unique way we find to avoid this catastrophic picture, then maybe we should do that, And public debt is always much less dangerous than private debt. Why? Because the state can go bankrupt and survive. A firm cannot go bankrupt. And so doing all this, so high and voluntary, very harsh carbon tax plus public subsidies would allow us to reach the net zero emission situation by 2075 and to have reasonable chance to stay close to +2 degrees at the end of this century. And I will stop here. Thank you.
Okay, thank you, Gaël. I think I might just ask a couple of questions here to help clarify or further explain some things to people. You mentioned the importance of fully dynamic macroeconomic models to couple to fully dynamic climate models. Sure. That's one seemingly inconsistency or that most integrated assessment models don't include. And you also discussed including the idea of debt, and that's what you kind of highlighted there at the end. Is it any kind of other insight you can give us, right? By not having macroeconomic models that properly account for debt and therefore interest payments, is this a reason why something like the Nordhaus model will generally not predict a collapse of the economy, or that the economy sort of always grows roughly no matter what the temperature is? So that's in addition to the damage function, so you can separate those two ideas.
Yeah, so there are four main problems in the Nordhaus DICE model. The first one is that the damage function is ridiculously optimistic, as I said. The second one is that it's not really a climate model. It's a very simple climate back loop. So what I showed at the end, which is a true climate model, is much more realistic from the viewpoint of climate scientists. Third, it's an equilibrium model, the Nordhaus model. So the unique representative household anticipates everything from today until the end of the history of the universe, which is of course ludicrous. And so there is no surprise. So he or she knows everything in anticipation, ex ante, and can adjust and adapt perfectly smoothly to everything. And fourth, indeed, there is no debt. So since there is a single household, he or she cannot have debt, because in order to have debt somewhere, you need two people, a debitor and a creditor. And so the fact that so many macroeconomists rely on the fiction of a single representative household is also a way to get rid of debts. So yet you just forget debts. Let me give you an example. In 2015, for the COP21 in Paris, where the Paris Agreement was signed, every country of the United Nations had to provide the organizers of the COP with what is called an NDC, nationally determined contribution, which is a kind of roadmap which describes the decarbonization path of that country. So a number of countries have done it, honestly like this, and a number of other countries have tried really to run some sophisticated mainstream models, including China. And China has done it with a model which has been built by Tsinghua University in China and MIT in the US. And so back then I was the chief economist of the French Development Bank, and we had funded the project, so I was allowed to dig into the model. And what I discovered is that in this model, which was apparently on the surface very sophisticated, you never had public debt, and you never had unemployment by assumption. This was a built-in assumption. So what I said to my beloved colleagues back then is that, well, you know, dear friends, I mean, your model is fantastic, very mind-blowing, but suppose that in order to really put into practice the NDC that you committed to implement, you need, which means, you know, for China, a peak of greenhouse gas emissions by 2030, and then a decrease. Suppose that in order to do this, you need like 400% of the Chinese GDP in terms of public debt, plus 80% of unemployment, because you're going to kill all the employments linked to coal mines, et cetera, then we know you will never do it because it's politically infeasible. My concern is that your model will never tell this to you because it's a built-in assumption that this will never happen in your model. So I'm just wondering, what's the use of this model? You know, very provocative question. So then our colleague from MIT was very, very furious and said, well, you're right, but you know, it would be very easy to add up debts and unemployment, which is obviously not true because these are intrinsically non-equilibrium phenomena, you know. And then the Chinese guy looked at me, had a small smile and said, well, you want some more tea, you know? So he had, you know, two reactions to the same problem. So, but this, I mean, I laugh when I say that, but at the same time, it's very serious because it means that the Chinese NDC is just a fairy tale because nobody has any clue about whether this can really hold water and whether it can really do it, because the model they have used in order to simulate this path of decarbonization is completely, has nothing to say about reality, you see.
Right. So is it a fair statement? You have, you know, experience in dealing with many more macroeconomic models and understanding frameworks than I do. And of course, you know, I try to learn from you. But my takeaway and what I've learned is that there's people maybe with more of my background training, like as an engineer or something, who are adding details about energy systems and prices and price curves or different technologies into economic models. They may be integrated assessment models. They may be not fully a full general equilibrium model or something. And when it comes down to it, the macroeconomic assumptions that are in the framework they're using that they're often unaware of are so simple and egregious that all the detail and all the time they spend working on these details are just thrown out the window. It's like, it just doesn't matter, right? The answer to the model is going to come out almost the same without those changes in details. That seems like kind of the example you just explained.
That's exactly true, unfortunately. And so that's a tragedy because we are lying to a number of students. They spend so much time, learning hard the nitty-gritty of microeconomic theory, blah, 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 all this. But at the end of the day, the big assumptions like rational expectations are so blatantly, you say that in English? Blatantly false that whatever being the sophistication of the other, myriad of assumptions you are going to add in your model, it would be completely wrong. I give you another example which struck me back then. When I was still in Paris working as a senior researcher at the CNRS, which you mentioned earlier, I had a student at the Sorbonne who did his internship with me. And so we started working on the Keane model, which I very roughly described earlier. And there is no rational expectations. So what is a rational expectations assumption? It's a hypothesis which claims that economic actors anticipate everything from today until the end of the history of the universe. And I've shown you, the graph of the IEA anticipation of the price of oil, so it's obviously not true, or the IMF's anticipation of the GDP of Greece. So it's not true that we have perfect anticipation, it's just obviously not true. But anyway, and then he had to defend his intern, he had written a small report about his work during the summer, and he had to defend this in a very famous French engineer school. And so the prof said, oh, what you have done is very good. And I was in the classroom to defend him, and the prof said, well, it's very fine, but, I'm very concerned because you haven't used the assumption of rational expectations. How come? So the student is embarrassed and said, well, with Professor Giraud, who is just behind me, we thought that maybe just for this very particular question, we would not need this assumption. Then the prof became very pale, completely, defeated, and said, that's a pedagogical failure. You are a student in this very famous school for 3 years. You haven't understood that you cannot articulate anything meaningful in economics without the irrational expectations assumption. And so probably he saw in the gaze of the student that he was not convinced. So he tried really the ultimate, pedagogical effort. So he said, and I'm not inventing, I could not invent it. He said, look, I just got a kid 3 months ago, a very charming young daughter, and I'm a responsible father. I'm her dad. I'm responsible for my family. So what I do is that I anticipate the price of oil until 2025 in order to understand her future. So he was turning this crazy assumption into a moral duty for him as a father. So in a normal society, we should have 2 guys with white clothing, running in the classroom, taking this guy, this prof, and putting him in a hospital. Because he believes truly that for his kid, he can anticipate the price of oil, while even the IEA does not do it, or completely fails in doing this. But this was a way to impress the students, So this kind of scenery is just insane. And we keep repeating this in many departments in economics, be it in the US, in Europe, Australia, China, I'm sure, et cetera, et cetera.
All right, we're going to work to change it. I'm going to have one final question here, which is kind of related to what we're discussing. I'll kind of read it here and then maybe elaborate. To what degree are the refinements that you've discussed in your presentation and these economic models essentially informing something like the integrated panel on climate change process? And are any of these kinds of models incorporated into those reports and processes? Just me speaking now. For the most part, the IPC kind of summarizes existing literature, I suppose, right? And most of what they're summarizing is sort of mainstream economic modeling, which, as you presented, is not sufficient. For example, can't predict a debt to collapse due to climate change, like you've shown. A model at least is capable of understanding that technique. So how much are these kinds of models kind of starting to get incorporated? And I mean, you're getting them in the literature, which means IPCC can start to quote them. You've got students at the World Bank now and some other places. So kind of how do you see the pace of incorporating this line of thinking in mainstream policymaking, I guess?
So right now, there is as we're talking, there is a kind of struggle inside the IPCC. IPCC is divided into 3 groups, group 1, group 2, group 3. So group 1 is essentially physicists who work on the science of climate. Group 2, a number of physicists, biologists, chemists, and economists who work on the consequences of global warming. Group 3, essentially economists who work on how to adjust, to adapt, and to mitigate. So, and physicists in group 1 have finally understood, 5 years ago, that economists in group 3 are telling narratives and stories which have literally nothing to do with science. And there is a big mismatch between group 1 and group 3, and group 2 is somewhere in the middle, you see. And so they are afraid because there is a big battle, an epistemological battle, but they don't want to show it publicly because it took so much time and so much effort to gain the trust of the public for the IPCC, and to have an impact on politicians, all this, etc., that if now they were showing publicly that they disagree fundamentally on what group 3 is saying, essentially, then this would probably undermine the credit that the public has finally given to the IPCC. They don't want this to happen. So they try to solve the problem, in the corridor and not in the big amphitheater. Pretty much in the same way, the big debates that took place during the pandemic in WHO were never made public. Or maybe there were big struggles among experts about what we should do against the pandemic. And nobody knew that except for a few people who were closely linked to the experts. So it's the same story for the IPCC. Now, what I showed you is not yet reported by the IPCC because we are publishing it now. So once we will have 5-10 papers in this area published, IPCC will certainly quote them, because I know a number of friends who are working for Group 1 and Group 2 and also for Group 3 who are just waiting for these papers to be published.
Right. I think when we first met at a conference, there was someone, I don't know if this was kind of a lead author of Working Group 1, I don't recall. And I remember asking that person, I was like, well, I asked him roughly the question you just posed. I was like, how do you feel that all of this detail and all this information you put into climate modeling is essentially thrown away by the economists in the other part of the report? And he just kind of hand waved. He wasn't sure what to say about it, I guess, about whether he was upset or not. But I said, don't you think this is a big problem? And so, yeah. Well, excellent. So again, thank you. This has been Gaël Giraud giving us a lesson in macroeconomics and implications for understanding climate change. He's the founder of the Environmental Justice Program at Georgetown University. So thank you again for joining us today, Gaël.
Thank you for inviting